Now, to study collinearity, we're going to need to understand something about the random vectors that we're using. So what are these random vectors? These random vectors are our feature maps psi of x for a random x. So we assume that we have some distribution for x, marginal distribution of x. We can assume instead that we have a density. We're assuming that we always have a density to keep things simple so we don't have to work with measures like this. Um, so this is what? This is psi 1 of x up to psi p of x. And I can put a transpose there to indicate that it's a column vector, but it's not too important. Each of these is a real valued function, right? Because our approximation f theta of x, our predictor, is the sum of these from I equals 1 up to p of theta I psi I of x. And this is a real valued function. These have to be real valued. So these are going to be random variables. Whatever x is, some random element, whether it's a random variable or a random vector, these will be real valued, so they'll be random variables. So this we call a random vector. It's a vector of random variables. And what's its expected value? The expected value of this with respect to this distribution or this density is just the vector of the individual expected values of the individual components. That's what it is. And we're assuming that this is 0. So this is equal to the 0 vector. So that means that each of these is 0. That's our assumption. And that will simplify things. It's without loss of generality, we can do this. So now we can say that the covariance matrix of our feature vector is the expected value of the outer product of the feature vector with itself. So what is an outer product? Well, an outer product of a vector, let's say u equals u1 to um transpose, and v is v1 to, let's say, k transpose, is going to be, well, it looks like this. So it's u, let's say, v transpose. Let's do it this way around. So what does that look like? Well, it looks like this: u1 to it's a column vector, times v transpose, which is a row vector. It's going to be v1 to vk. Well, what is this? In terms of matrix operations, right? So this is a matrix operation, considering these as matrices, or identifying them as with matrices. Looks a bit strange because we're used to u transpose v, where these live in the same space. So in that case, m would be equal to k. That gives us a number, a scalar. Well, this is something different, right? So this kills a dimension. This grows a dimension. This takes two arrays of length k or m. They have to be the same. It gives us an array of 0 dimension. It's basically a number. This takes two arrays of one dimension and gives us an array of 2 dimensions, a matrix. So this will turn out to be a matrix, which is equal to this matrix here. It's all of these times v1. So it's u1 v1 down to um v1. And the last column will be u1 vk down to um vk. So that's what an outer product is. Now, the variance covariance matrix of this, or simply covariance matrix, we call it the variance covariance or covariance matrix of this random vector, of any random vector, is defined as a matrix of the covariances of the elements of this random vector. So The covariances are of this form: psi I of x and psi j of x. Right? Now, if we put I equals j, this becomes a variance. So along the diagonal, we're going to get the variance of psi 1 of x down to the variance of psi p of x, right? And in the off-diagonal terms, we're going to get here covariance of psi 1 with psi 2, and here we're going to get the covariance of psi 2 with psi 1. But these are the same, right? The covariance operation is symmetric. Doesn't matter which way around we put these. So these are equal. And we'll have the same throughout. And so this will be a symmetric matrix. Symmetric matrix, right? Now, what is the covariance? The covariance of this here, of this is, let me remove that. I've already written it down. This is equal to the expected value of this. So these two are random variables of psi I x minus its expected value, psi I of x, right, times psi j of x minus the expected value of psi j of x, right, close bracket. But the expected values are 0 because of this assumption. So the expected values of this is 0 and the expected value of this is 0. And so we get the expected value of this times this, right? So here, these are going to be the expected value of psi 1 times psi 2, right? Which is exactly the same as this. And this will be the expected value of psi 1 times itself, expected value, so on and so forth. So this is why we make this assumption. The covariances become simply the second moments. Okay, now we can reproduce this matrix that I just described using this outer product, this expected value of this outer product. Right? It's just a compact way of writing the covariance matrix. It turns out that if we form this outer product of this random vector and itself, and we take the expected value of that outer product, what does that do? That takes the expectation inside to each of the terms. So this outer product, the first term would be psi 1 of x times itself, right? And we take the expectation, so the expected value of this goes inside the matrix, and it's defined as the expected value of each of the elements of the matrix. So this becomes this, which is the variance of psi 1. And here we'd get the expected value of psi 1 times psi 2, which is the covariance of psi 1 and psi 2. And in the general case, it would be the covariance with the expected value of psi I, psi j, times psi j, which is the covariance of psi I and psi j. So this is just a compact way of writing this variance covariance matrix because it's reproduced by the expected value of this outer product, which is a matrix, and we just take the expectation inside the matrix. This is all explained in the probability videos. Now, entries of this covariance matrix, as I say, are the covariances of features I and j in our feature vector psi of x for some random x. And these are going to be non-zero only if these are correlated. So this, if psi I and psi j are correlated, this covariance will be non-zero. Or equivalently, we can define a correlation, right, which is a normalized covariance. In sample terms, we have this matrix here. So what is this matrix? This is the matrix that appears in our Moore-Penrose pseudo inverse, our solution. And what is it? It's a sample covariance matrix. The covariances of the features, these psi i's. It's a sample of it, and it's well, it's if we put n minus one here, it's unbiased. Right? So what does this look like? Well, psi is let's put psi here. Phi, not psi. Phi. So phi is the row of the feature vectors at each data point. So we're going to get here psi 1 at x1 and psi 1 psi 2 psi 2 at x1 and so on down to psi 1 at p at x1. This is 2. Right? And here we're going to have psi 1 at x2 down to psi 1 at xn. Right? And this is the transpose. So this is phi. And this matrix here is going to be phi transpose. So it's going to be psi. So let's think of what's going to go along the top here. We're going to get now columns. So this is going to be psi. Let me get this the right way around. We're going to get psi 1 at x1. Going to get psi 1 at x2, and so on, psi 1 at xn. And down here, we're going to get psi 2 at x1, right? Down to psi p at x1. Right? That's what we're going to get. So what would be the first term of this matrix? This times this. Well, this term here is going to be the dot product of this vector here with this vector here. So we're going to get the sum of psi 1 at xi. Right? So we've got x1, x2 up to xn, x1, x2 up to xn, from I equals 1 up to n. Right? If I put a 1 over n here, this is a sample variance. Right? If I put n minus 1, it's unbiased, but if I put n, it's a biased sample variance of psi 1, the random vector, psi 1 of x. So this is a sample estimate of the variance of this. Now here we're going to get a sample covariance of psi 1 of x and psi 2 of x, right? And so on and so forth. So this thing here divided by n, or n minus 1, is going to be a sample covariance matrix. It's a sample version of this thing here. Right? We're assuming that each of these has 0 mean. So correlated features are going to correspond to off-diagonal elements of this matrix being non-zero. Right? So if off-diagonal elements of this are non-zero, we know that these features, these psi i's, are correlated, or those that are non-zero will correspond to correlated features. So what does this mean in terms of our geometry, our contours? Well, these are our contours of empirical risk. And what do they involve? They involve this matrix here. Right? So if these off-diagonal entries are non-zero, we will get rotated ellipses. Why is that? Well, let's have a look. Let's have a look at a simple case. Let's say that we have some. I'm going to just keep things simple. I'm going to replace this with just some general vector x. So let's say x transpose a times x, right? And let's say x is a vector with only two components, x1 and x2. Right? So A is a 2 by 2 matrix. Well, if A is diagonal, what does this look like? This looks like, so x transpose is going to be x1, x2. and let's say A is A 1 0 0 A2. So it's a diagonal matrix. The off-diagonal entries are 0, and then we're going to get x1, x2. This is going to be equal to, so if you multiply this whole thing out, we'll get a1 x1 squared plus a2 x2 squared. Right? And if we set this, so this is the equivalent of this, where I've just replaced this with an x. This is an x transpose, and this is just some a, which happens to be diagonal. And if we set this equal to a constant, we'll get these contours. What's this? Well, if A1 is equal to A2, we'll get a circle. All of the points x1, x2 that satisfy this constraint will lie in a circle. If A1 is not equal to A2, we'll get an ellipse. What kind of ellipse will we get? We'll get one that is aligned along the axes. So it will look like this. So it will either be aligned like this, it will look like this, or it will look like this. Right? Now, if these are not 0, let's say B1 and B2, then this will contain cross terms plus, blah, 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 x1, x2, plus some other constant which is then absorbed into there. And in which case we will get rotated ellipses like this or maybe like this. Right? So the ellipses won't be aligned along these x1, x2 axes in that case. So correlated features correspond precisely to that case. Rotated ellipses. Uncorrelated means the off-diagonal entries are 0. We'll get ellipses which are aligned along the axes.